Actually, I'm not Subrata Kumar. I'm Shovan Bhaumik from IIT Patna, and bearing only tracking considering dynamics of toad array. This work has a story. So let me tell the story first. So this is actually an engagement scenario. So we have ships. We know all the ships we have, and ships need to measure the position of other ships. Okay, and for that, what they do, they use sensor, which you call sonar. So here it is the sensor. But sonar, we use passive sonar because we don't want that this enemy ship detects ours. So, but if we use passive sonar, basically what passive sonar does, it takes the energy from the other ships and all and calculate the angle. Now, if we put this sonar near the ship, what will happen? It will take the propeller of the ship energy and it will detect. So you can do. Okay. If you can do. Okay. So if you see that, if you don't put that cable, if you put this one here, what will happen? The ship propeller will move and the sensor array will take the noise from it, energy from it, and it cannot detect the target here. Rather, it will detect the own ship. So it will be the interference. So what people used to do, they used to put a long cable. It is around 700 to 800-meter long cable. And then they have a sensor array, so which is around 200 meter. So total combined this cable plus array, it is 1 kilometer. And there is a pulley behind the ship. So usually when there is no measurement required, they put it on the pulley. And then when there is measurement required, they open that pulley and it gradually goes inside the water. Now the interesting thing is that, so when it is inside the water, then it can measure. But sometimes what is required, this own ship is turning or taking a maneuver. Then what will happen? If you imagine the tail of a kite, if the kite changes its position, the tail changes its position. So if the own ship is taking a maneuver, then this tow cable also will not follow the own ship path. So if it is not following the own ship path, then what will be the position of the sensor so that we can easily determine the target motion. This is very interesting work and nobody previous to this attempted this. What people used to do when this own ship is taking maneuver, they just stop updating the measurement. They think that okay, the own ship is taking maneuver, there is some disturbance in the tow cable and sensor array. Let's wait and let's own ship take the maneuver, completes the maneuver and then move straight so that again the sensor array will be stabilized and then it will be just behind the own ship. So the position of the array can be known. So in this our work, what we did, we tried to do a dynamic modeling so that if we know the own ship position and if we know the different dimension of the towed cable and sensor array, can we say what the sensor array position will be at any point of time when own ship is taking a maneuver? So that is the problem statement of this work, and we started doing it. So what we did, so we started doing this mathematical modeling. This is kind of first principle, Newtonian motion, torque balance, all these things. So we assume that rigid body is the body is rigid, towed cable and the array segment is rigid, and that there is no current in ocean water. The water is still, and there is no other disturbance. And there the drag which is there, that drag is constant. Okay, that there are two parts of the drag, normal drag and tangential force drag. So they are considering to be constant irrespective of the angle of attack. Angle of attack means the angle it is maneuvering. So now this is the way we did. What we did, the whole cable we divided into two parts and the sensor is another part. So total three parts we divided and we try to calculate what are the force balance equation and movement balance equation. And that is a typical dynamics of mechanics. So, but we need to go through this, otherwise we cannot model this tail. So we did the modeling with the movement balance equation and then we did it with the this is all for the drag force calculation, and ultimately we came out with the calculation or a mathematical model which we can tell what the tail or the sensor will take path when one ship is maneuvering. We know the path of the maneuvering ship. So we solve this using some integral. It will come in the in between. We solve it using some Gauss-Legendre point method, which is the numerical integration method. Okay, and then we solve the differential equation using the fourth order Range-Kotta. And there is a process model of the target, how the target is moving. There is a measurement. We take the bearing measurement, that means at the angle of it. And then we calculate, we consider the scenario, and this is the exact scenario. This one I want to focus. If you see there is a straight line here, there is a straight line. This is actually the target. Target ship is starting from here and it's going straight like this. This is our own ship. Initially it was going straight. When it was going straight, the tail is following it. So these colors are actually the segment of the tail. Now when it start taking maneuver, you see the tail gets deflected. So these are the tail motion when the ship is taking maneuver. And once, and again, this is the tail motion. Once the maneuver completes, then this tail motion again following the ship. So this one we exaggerated. So we have the three number of segments, 1, 2, 3. And when the ship is taking maneuver, how the segment will go. And so now what advantage we get? So at each point, we know the middle of the sensor, and then we know from which point we will consider the signal processing and which point is measuring the angle of the target ship. And we can start signal processing considering the sensor location in this point. If we don't do this modeling, we don't know where the sensor location is, and we cannot do the sensor or signal processing quite accurately. So we did this modeling, mechanical modeling, along with the signal processing. And signal processing, there are several estimation methods are required, and we make it repeatedly. We do the estimation, and then the error we calculated, root mean square error with respect to time. We see that the root mean square error is decreasing. This is root mean square of velocity with respect to time. We see that it is converging. There are many estimation methods that I don't think it is we should discuss it here. Anybody is interested, I can discuss separately. And these are the table where we see that what are the position and velocity at last point is achieving, or average RMSE. We take the RMSE and we average it. So we have a position, we have a velocity. So, and we take the time T for 30 minutes, 30 seconds, 60 seconds, 30 seconds, 10 seconds. These are the sampling time. And with respect to that, we calculate this. And these are the percentage of drag loss. So with the estimation method, what the drag loss we are getting, and we see that our methods with the dynamic modeling drag loss is less. And these are the conclusion that the bearing only techniques during on-ship maneuvers, either we have to halt because we don't know the sensor location, or we can continue with assuming that the sensor are in a straight line. Both are disadvantageous. If we halt, our signal processing will halt. And if we assume the straight line motion, that is erroneous, because during the maneuver, it is not a straight line, rather it is taking a different shape. And in this way, we could know where the sensor location is, and we could do the signal processing more appropriately. So this is the contribution. And result shows that our method is showing that more accurate estimation and very less number of drag loss. So these are the reference. Thank you.